Hello everyone, welcome to recitation number 4. The topics of limits at infinity and continuity. You know that horizontal asymptotes belongs to limits at infinity. We have just a bunch of problems for today. You should always try to solve the problems before watching me solving them. So this is a moment for you to pause the video and try to find these limits. But I'll be finding them now. What happens with the limits here? What you should not do is trying to essentially plug in infinity inside of the expressions. Because for example, in the first one, 3 times infinity, 2 times infinity, minus 1. What is this limit going to be? Okay, so for example, upstairs you have actually minus infinity plus infinity. In theory, we don't know what that is. In practice, we actually know what that is. If you look at the polynomial for right here in this problem, the x squared term is the dominating term here, and it's negative. So the top side here would be a minus infinity. This minus 1 here, this plus 2 infinity are irrelevant. Similarly, the bottom would be a plus infinity. But this is a problem. Usually you don't want to try to find limits of the form infinity over infinity this way, because that's called an indeterminate form. This could be anything. So that's not how you solve these problems. How do you solve this problem? This is what's called a rational function, ratio between two polynomials. What you should do is try to divide by the highest degree in the denominator. Divide both expressions. Sorry, both numerator and denominator. So we're gonna be dividing by x squared. For example, x divided by x squared gives you 1 over x. And now, as you take x either to plus or minus infinity, it doesn't matter. All the terms that have number over x, they actually go to 0. So the limit as x goes to actually either plus or minus infinity, let me call the function f of x, is actually going to be minus 3 plus 0 minus 0 divided by 2 minus 0 plus 0. That's just minus 3 over 2. Those are actually already the two things that were being asked in this problem, the limit at plus and the limit at minus infinity. They are the same. Next problem, find this limit. We have here a difference of fractions. If you look at each specific fraction, x is going to infinity, and the polynomial that appears in the numerator has a higher degree than the denominator. This means that the numerator is dominating over the denominator. It's trying to make the fraction larger and larger. So each one of these fractions is going to infinity. And the answer is then infinity minus infinity. But what is that? You cannot just say this is 0. Don't do that. Infinity minus infinity is also indeterminate. It could be anything. There's no question about that. One of these infinities might simply be too much larger than the other, causing the expression to be infinity or minus infinity, or maybe not. Maybe they have similar sizes and this goes to a number. But anyway, we cannot do that. We cannot do infinity minus infinity. We have to somehow simplify the expression. And it should be clear what to do here because it's a difference of fractions. Let's compute this difference. Take a common denominator. In which, in this case, both of the denominators are just linear expressions. Our common denominator will simply be 1 times the other. So at the top, you're going to have 2x squared times 6x plus 1 minus 3x squared times 4x minus 1. Let's see what this gives us. I'm going to expand out everything 12x cubed plus 2x squared minus 12x cubed minus 3x squared. And what do we have downstairs? Distribute out 24x squared plus 4x minus 6x minus 1. Okay, look at the numerator. The 12x cubed appears twice. That goes away. And you have 2x squared minus 3x squared. So this will just be minus x squared. And what is happening downstairs? You have 24x squared plus, I just realized I have a typo. You may have already seen it. Good thing that I just realized it. It's the 3x squared term. When I distributed it, I'm gonna fix this in red. When I distributed it inside here, that should have been a plus 3x squared. So actually it's a 5x squared at the top. I remembered this answer. But continuing, the denominator here should be fine. 4x minus 6x is minus 2x, and then minus 1. All right, this is the expression. That's the one whose limit we're trying to find as x goes to infinity. How do we do this? Once again, this is a ratio between two polynomials. And you cannot, again, you cannot plug in infinity to get infinity over infinity. That's indeterminate. What we do for this is divide by the highest degree of the denominator. Usually you want to do it for the denominator, but really it doesn't matter if you do highest degree of numerator. That can also be helpful. Essentially, you want to do something that gives you a helpful result, like this one. For this one, now if you're trying to find the limit as x goes to infinity of this expression, f of x, whatever. Well, because x is going to infinity, the expressions 2 over x and 1 over x squared are going to 0. 1 over a large number is a small number. So this leaves you with a 5 over 24. Moving on. This is again a similar type of problem with the rational ones, rational functions. This one is not a rational function because there's a square root. But how do we think of this intuitively? Well, essentially the highest degree in the numerator is an x and not an x squared. You have an x squared inside of the square root, but after taking a square root, this numerator has approximately the size of x when x becomes large. And similarly, the denominator also has an approximate size of x. So we expect to find a number for the answer here. And this one can be tricky because of minus infinity and square root of x squared. I'm once again reminding you about this fact, about the fact that square root of x squared is not x, but absolute value of x. We're definitely going to use this here. So what is the solution to this problem? So the highest x power in the denominator is x to the 1. It's just x. We're going to be dividing by that. There you go. So, okay, so we've divided both numerator and denominator by x. How do we fix this now? How do we simplify the numerator with the square root? You know that what's gonna happen is essentially this x squared term, we kind of want to factor that outside of the square root, bringing it as in the form of x outside, so that then it cancels this 1 over x. That's what we're gonna do. So I'm gonna factor an x squared inside of the square root. Sorry, I should have written the x squared first. There it is. 2 plus 8 over x plus 8 over x squared. The whole thing divided by 5 minus 4 over x. And now I'm going to bring the x squared outside of the square root. Namely, you can write this, first of all. You have a square root of a product. You can take the square root on each term. And this is the place where I told you we have a square root of x squared. We want to write that as absolute value of x and not as x. And now let me again scroll back up so you can see what is the limit that we're taking. X is going to minus infinity, which means we're only interested in numbers x which are very large but also negative. This means that this absolute value of x right here, we can replace that with minus x. So I'm going to write that this is equal because x is negative. X right here in this limit problem represents a negative number that's getting large. So the expression itself actually simplifies down to this. And now you can see this minus x with this 1 over x, they make a minus 1 together. This is now in a good place for us. When you look at this simplified expression now, you realize this is one for which you can simply calculate the limit as x goes to minus infinity. What does that give you? There's a minus sign outside. Square root at the top, it's 2 plus 0 plus 0. And in the bottom, it's 5 minus 0. Once again, a number like 8 or anything that's not 0 divided by x, as x goes to either plus or minus infinity, doesn't matter, that fraction goes to 0. And this limit is just minus root 2 over 5. That's the answer to this problem. So it's a problem where we are also using this trick of identifying the highest power in both numerator and denominator, somehow factoring that power to make an expression for which you can see the limit appearing not in an indeterminate form. Problem 4 is very similar to the previous ones. We are again going to factor somehow a highest degree term. But as turns out, which one is the highest one is going to depend on which limit you're taking. This is why this suggestion is given here. But first, let's read the problem. They didn't give us a limit to compute. They said find the horizontal asymptotes. That means we're going to need to find the two limits at infinity and minus infinity. We want both of these guys. If we can find numbers for them, then we have the two asymptotes. If we don't find numbers, then there are no asymptotes, or maybe there's numbers just for one of them, not the other. But the suggestion is saying explore what happens if we factor either e to the x or e to the 2x in both numerator and denominator. So we're going to do exactly that. Before taking a limit, let's see what's going to happen. I mean, it's clear that if you try to take a limit, either plus or minus infinity, you run into trouble with the expression. For example, let's imagine we're taking a limit at plus infinity. Then you have infinity minus infinity divided by infinity plus infinity. That's a very indeterminate expression. Whereas if you're taking x to minus infinity, you know that e to the x and e to the 2x are going to go to 0. E to the minus infinity is 0 in symbols. So then the expression would actually be 0 minus 0 over 0 plus 0, which is again indeterminate. That's why we know that we need to do something to factor. So what is going to happen if we factor e to the x? Let's see. 1 minus. How do we factor an e to the x from e to the 2x? What is e to the x? E to the 2x, removing a factor of e to the x, that is actually e to the x. Don't say it's e squared. because what you do here is you subtract the exponents. So be careful about this. And similarly, downstairs, we'll give you a 2 plus 3e to the x. So after factoring e to the x, we get this expression for the function. What's happening is that now this form of it is going to be useful to compute one of these limits. Try to figure out which one it is. In this form, we can immediately find the limit as x goes to minus infinity. Because e to the x is going to 0 as x goes to minus infinity. This is one of the limits that I mentioned as the last slide on my lecture. The end behavior of exponential functions. E to the x, just remember the graph of e to the x. Looks like this. As x is going to minus infinity, e to the x is going to 0. So this limit can be computed as 1/2. So we found the limit as minus infinity, as x goes to minus infinity. If you want to find the limit at plus infinity, the expression, even though this expression is correct for the function, it doesn't help you, because if you plug in x equals plus infinity, then that limit is still of the form infinity over infinity. It's still indeterminate. But the suggestion that the problem gave us was try to also factor an e to the 2x. Just see what happens. So let's see what happens. So factoring e to the 2x from e to the x leaves e to the minus x behind. Just think about what would happen if you tried to distribute this expression here. E to the 2x times e to the minus x would give you the e to the x. And downstairs, similarly, 2e to the minus x plus 3. So if you factor e to the 2x from the function, this is the expression you find. This expression now is useful to find the limit at plus infinity. What is this limit? Well, where does e to the minus x go as x goes to plus infinity? What is the graph of e to the minus x? If e to the x looked like what I just drew, e to the minus x just reflects that around the y-axis. This is e to the minus x. The limit at plus infinity is 0. So this gives you a minus 1/3. Very cool. We found those two values. Why were we finding these values? Remember that the problem wanted us to find the horizontal asymptotes. We found two values. That means there are two horizontal asymptotes. There are two horizontal asymptotes. At those particular two values, y equals 1/2, y equals minus 1/3. It's always y equals the value because it's supposed to be a horizontal line. Next problem, find this limit. First thing that you should think about when you see the problem, trying to understand the limit separately. Both functions are trying to go to plus infinity. I hope that's clear. If you take very large numbers x in here, that expression just grows without bounds. Similarly for the other one. So this would actually be an infinity minus infinity indeterminate. We cannot do it this way. If this minus was a plus, then yes, infinity plus infinity is infinity. That would be the answer. That's just that. But because it's a minus, we have to do some work. What is the work? Well, difference of square roots, or more precisely, difference of two terms, at least one of which has a square root. You should always try to rationalize it. Or which is the same thing, multiply and divide by the conjugate. That's what I'm going to do here. Why do we do this? Now, when you expand out the numerator, you have an expression like a minus b times a plus b. The simplification of that leaves a squared minus b squared. And the square gets rid of the square roots. So that was the difference of squares in the numerator. We can cancel this now. You see that the x squared will go away. You are just left with 3x minus 2x. So that's a 5x at the top, divided by nothing to do at the bottom here. It's certainly not true that we can combine the two square roots into one. No, the sum of square roots is not the square root of the sum. But okay, we have now this expression. It's at least now a fraction instead of a difference. This is much better. But it's still indeterminate. We're trying to take x to plus infinity this time. We still should believe that there will be a number for the answer. Why is that true? The numerator has degree 1, and the denominator in some sense also has degree 1, because we have quadratic terms, but they are under square roots. Each one is like a linear term in size, at least. So we believe that the two numbers are comparable in size, and they should be going to the same values. So what am I going to do here? I'm going to factor x squared from inside the square roots, each one of them. X squared times 1 plus 3 over x. And the other one is x squared times 1 minus 2 over x. I'm not multiplying and dividing by anything, although we could do that as well. Instead, I'm actually just factoring x squared from the expressions. They are the same now. I mean, the expression that I got here is the same as I had. And now I'm going to take the x squared from the square roots outside of them. Once again, remember, the square root of x squared is absolute value of x. But this time, because we're taking x to plus infinity in this problem, absolute value of x is just x itself. So if you want to justify this step, because x now is positive. And what happens in this expression, if you see that you can factor an x from the sum in the denominator, you have a sum of two terms, each one containing an x. Factor that x, and then cancel it with the one upstairs. You're left with 5 over the sum of these two roots. So that was the whole expression being simplified. What is the limit now as x goes to infinity? Well, 3 over x goes to 0. Minus 2 over x also goes to 0. So 5 over root 1 plus root 1, 5 over 2. I encourage you to plug in large values of x in this expression. Take x equals 100, take a calculator, see what happens. Take the square root minus the other. You're going to find a number that's very close to 2.5, which is 5 over 2. If you don't, that means we have a mistake somewhere. Okay, now we are kind of in the same topic still, but I'm mixing in some continuity. Look at this problem. Find this limit and justify your answer using a fact about continuity. take a look at this limit. X is going to infinity. The expression involving x is now inside of a sine function. When you look at this, you should think of the sine function as the outside function. And you kind of want to move the limit sign inside. Well, we've seen results that tells you that this can be done in most cases. When exactly? As long as the outside function is continuous. More precisely, it just has to be continuous at the point which is going to be the limit of the inside. But this really doesn't matter here because sine is a continuous function everywhere. So you start by saying, because sine is continuous, which means continuous at all points, the limit is the same as this. Move the limit symbol inside. And now we really just need to worry about the limit inside. You should be able to guess what the answer is, but you should never just write it in your solution without explaining or without indicating what the calculation is that you're doing. What is the calculation here? If x is going to infinity, you want to factor this power of x from both numerator and denominator, which means divide both by x. Because when you do that, then you can calculate this limit. 1 over x goes to 0, 3 over x goes to 0. So you'd really have 2 pi over 2 sine of pi is 0. This is the answer. How do you think about this? Really, you just had an expression inside of sine. That expression was going to pi. That means when you take sine of that expression, it should be going to sine of pi. That's the meaning of continuity of sine. And sine of pi is 0. Now a question, we actually never talked about the absolute value function in terms of continuity. Is this function continuous at 0? The question wants you to determine this. If you had to guess, remember our informal notion of continuity, it means the graph does not break. Well, this is the graph of the absolute value function. We should know this, by the way. It's just this V shape. And it looks like it does not break. There is no problems around there. There's no jumps of the graph. So we guess that it is continuous, and this is actually the answer. It is. But how do we check continuity? Remember, we actually have a definition for continuity. 3 things to check. We must check, first of all, that f of 0 exists. It is well defined. What is f of 0? Absolute value of 0 is 0. So the function is defined there. What about the limit? Does the limit of f of x as x goes to 0, does that exist? How do we know that it does exist? Okay, f of x is the absolute value function. You know that this is, when you have absolute values, you should not automatically plug in the number 0 in there. You should be very careful about that because the function changes depending on which side you're coming from. So anytime that happens, you should not just plug in automatically because you were trying to determine continuity here. So the plugging in is very sketchy. You should not try that. Instead, you should try to verify the limit by computing the one-sided limits. But this is very easy. If x is going to 0 from the positive side, that means x is positive. So the absolute value is just x, giving you a 0. And if x is going to 0 from the left, then the absolute value of x is minus x. But the limit of minus x, as x goes to 0, is minus 0, which is 0. They are equal to each other. That's why the limit exists. Hence, Not only it exists, but also it is equal to that same value, 0. And the third condition that needed to be satisfied is this: the limit exists, and it should be equal to the value of the function. This is true because both are 0. We just computed both of them. They are equal to each other because both are 0. So I guess there's a lot of zeros in this problem. I should probably circle the ones that we care about. It's this one, the value of the limit, and also this one, the value of the function. Both are equal to each other. Then yes, all three conditions are satisfied. F is continuous at 0. By the way, not just 0, but anywhere, at all points, this function is continuous. But 0 was the most problematic one. If you wanted to verify continuity at the number 2, for example, just so we're clear, then it's fine to say around the number 2, the function is equal to just x itself instead of absolute value of x. Around the number 2, it is a polynomial function. So we already know that kind of function is always continuous. Really, that is not where the problem is. Next question. Find the horizontal asymptotes of e to the minus x to the 5. In other words, if the question asks you to find horizontal asymptotes, it means they want you to find both limits at infinity, both plus and minus infinity. If you manage to find a number for any one of these, then that will be an asymptote. You can have at most 2. So we need to find these limits. This question is here just so we understand how to think about it. There are many possible answers here. It's almost like plugging in the value. It's almost like plugging in infinity and minus infinity. So it's fine if you write something like this, for example. Imagine you're trying to find limit as x goes to infinity. You can write this, e to the minus infinity to the 5. It's like plugging in infinity for x. If you want to be extra careful about justifying, you should say the outside function, which is the exponential, e to the something, that's a continuous function. Therefore, you know that it is possible to just plug in the value, even though this value is infinity now. So this is kind of an informal calculation, but that's fine. What does this become now? First of all, what is infinity to the 5? That's just infinity. In other words, a large number and positive raised to 5 is also going to be a positive large number. And what is e to the minus infinity? Remember the graph. If x is going to minus infinity, the function is going towards 0. So this is the first of the 2 limits. Should probably be intuitive to you. Imagine plugging in a really large number here. E to the minus that will be very small. And what is the limit as x goes to minus infinity? Be careful with your parentheses here now. There is a minus on the function, but now x is minus infinity. And we're going to do the same reasoning here, but what is minus infinity to the 5? That's also minus infinity. In other words, a really large but negative number raised to 5 will also produce a really large number and negative, because 5 is an odd power. Negative to the odd power is negative. But together with the other minus in the function, this produces a plus infinity. And what is e to the infinity? That's infinity. Look back in the graph. So those are the 2 limits. Only one of them was a number. only the number 0. The other was the symbol infinity. So that means that this function, I should probably write e to the x here. The graph that I drew was for the function e to the x, not for our function f. Our function f has only one horizontal asymptote. Y equals 0, the only one for which there was an actual value for the limit. The actual, and it happened when x was going to plus infinity. The actual graph of our function is something like this. This is f of x in this problem. As you can see, as x goes to minus infinity, it is going to infinity. Next problem, a very common type of problem for continuity. I had a little typo here. It should be a lowercase a. So I'm giving you a piecewise defined function. F of x has two possible definitions, and the breakpoint is -2. But inside of f of x, there's a parameter called little a that we don't know. And they're asking, what is the value of this parameter that makes the function continuous at -2? Idea for this problem, what is the intuition? The function has two different pieces depending on whether you are before -2 and after -2. By changing the value of a, those pieces will change form and also where they are. And you want to find the a that makes them meet at the same point. There should be only one value in this case, but in general, there can be more than one value. That's the idea here, but how do we actually do that? Just remember that continuity means three different things that have to be checked. The first two being usually either too easy or already determining the problem. First of all, f of 2 exists. And what is that? What is it actually? The function is defined at 2. You should be able to tell me what f of 2 is looking at this definition. F of x depends on whether x is less than or equal to, I should say -2, not 2, sorry. So once again, f of x depends on whether x is less than or equal to -2 or greater than -2. Well, -2 is less than or equal to -2. We need to use this first expression for it. So I'm plugging in -2 for x. This will be 4 minus minus, so plus 2a. That's f of -2. What about the limit? Does that exist? Well, this is a piecewise defined function where the break happens exactly at this number, -2. We need to analyze this from both sides. If you come towards -2 from the left, then you need to use the first expression for the function, which is x squared minus ax. And plugging in a -2 here, we've done this already above. This will give you the value 4 plus 2a. Now, if you come towards -2 from the right, the expression that you use for the function will be x plus a. And what happens when you plug in x equals -2 here? It's just -2 plus a. Are they equal? Well, we don't know. We don't know what a is. In fact, the problem is asking us find the a for which the function is continuous. We want them to be equal so that the limit exists. So we can write something like, if we want continuity, then these two must be equal. Otherwise, the limit will not exist, so the function will not be continuous at that point. Now, this is an equation for a. That's very easy to solve, by the way. A equals -6. So we found the value of a that at least it makes both the first and the second item true. If a is 6, then actually the two one-sided limits are going to be equal. And the limit itself exists. X going to -2. What is the value of the limit going to be? It's going to be the value of either one of those one-sided limits. For example, take the second one, -2 plus a. That's going to give you a -8. You could have also taken the first one. That's also going to give you a -8 because we imposed that the two should be equal. So here is the value of the limit. Let me go back and circle the value of the function. We found that to be 4 plus 2a. But remember, there's a third item. This one is where you have to check that the two things are equal. We just found the limit and we found the value of the function. Are they equal? Well, yes, for a equals 6 or -6. Is that right? Is that the value that I found? For plus 2a, that makes more sense. 4 plus 2a was the value of f of -2. And if you plug in a equals -6 here, then 4 minus 12 is -8. They really are equal. So the three conditions are satisfied for that value of a. So a equals -6 is the value. The value that makes the function continuous. So this may have looked like a lot of steps just because we are trying to be careful with checking all three conditions. But if you really think about it, all that we have done was ensure that at the value x equals -2, the two expressions should be equal to each other. If that happens, then the function was continuous at that number. Now I have a similar problem to this, but where the parameter is given in a different location. The parameter is called big B in here. What are the values of the parameter that make this following function continuous at big B? So there are two expressions for the function, but the place where it breaks is unknown. It's a B. Now just try to imagine what could happen here. Both of these are parabolas. We don't really know if we don't want to think too much about them. Don't really know where they are. But there are two parabolas that might meet in two different locations. So for example, if your B, the breakpoint, is this first location where they meet, that means that, for example, before that point, your function is equal to one of the two parabolas, and after the point, it's equal to the other. This would be a continuous function because they meet. The change in behavior happens exactly where they meet, so it's continuous at that point. Whereas if this break B happened anywhere else, so not this point and not the other point, then it would be discontinuous. So in other words, what is this problem going to be about? It's going to be about finding the places where the two parabolas meet. But let's see that coming out from the conditions of continuity. Okay, we wanna find continuity at B. The first item is obvious, f of B exists. That's fine. Really, let's not worry too much about even if it's what is the value, but that's easy enough. What is f of B? Well, f of B, according to the definition, is b squared plus b minus 1. You have to use the second one because this is the one that applies to B itself. Now limit as x goes to B. Does that exist? Well, that depends. We're going to need to check both of the limits. B is this point where the break happens. So in order to compute this limit, you need to compute both one-sided limits. And in principle, you're going to find two separate values for them, unrelated, because they're going to depend on the B itself. What is it if you're coming from the right? 2x squared minus 7. No, sorry, this is from the left. If x is less than b, you have 2x squared minus 7 for the expression. Plug in b here will give you 2b squared minus 7. What happens if you're coming from the right? Then you have to use the other expression. The x squared plus x minus 1. B squared plus b minus 1. Of course, in principle, they look like two different numbers. They are going to be different for most cases, but not all. There may be a few values of b for which they are equal. Those are the ones that we want to find. We want them to be equal. So solve for b here. I'm going to do that quickly. This is a quadratic equation. Moving everything to the left. You're looking for two numbers whose sum is minus 1 and product is minus 6. Minus 3 and plus 2 does the trick. So you have two values for b, 3 and minus 2, giving you a match here, giving you equality. So so far, those are the only candidates for us that make continuity. If you're not at these values of b, the two one-sided limits are not equal, so there is no limit. But if you are, if b is 3 or minus 2, then the two values there are actually going to be equal to each other. So you can say that the limit exists. Finally, for the third item, this is going to be true. There's some things to be checked here. Remember, what we have to do is the value of the function equal to the limit as x approaches b? Is it true? Check this when b equals 3 or minus 2, the only two values that we had, and it is going to be true. So for example, if b is, let's say, 3, I'm going to go back here. We already found the value of f of b, b squared plus b minus 1. If b is 3, this is just 9 plus 3 minus 1. You have a value for that. Whereas in the second item, if b is 3, the value of the limit is either one of the two one-sided values, which are going to be the same. So that also is a value that you can find, and you're going to see that they are equal to each other. And the same thing will happen with minus 2. So this is true. We'll leave this for you. This check is just checking. So the answer is really those two values. Basically, after you reach this third point here, it will always work. If you already managed to get the two one-sided limits to coincide, so you already found possible values for b, then the expression here, as long as you have just two pieces for the function like this, you don't actually have an extra value when x equals b, then it works out. Now this is my last problem here. I'm not going to give you any exercises like this. If you want to skip this, that's fine. The limit itself is going to be very simple. I just wanted to talk about this briefly, the concept of a slanted asymptote. As I told you, this is unlikely to show up on any exams. We're really not covering this topic. I just wanted to tell you what it is in terms of a problem, an example problem. So in this problem, consider the function f and also another function which is a line function, a function whose graph is a line. I'm giving you this f and this L. The problem is telling us that L is a slanted asymptote of f. And they're saying because turns out as x approaches infinity, the values of f are going to get arbitrarily close to the values of L. This is something that you can check if you try to graph. Imagine the line 5x plus 5, something like that. As it turns out, the function f approaches that line. Now, just looking at it, I don't know if it's approaching from below or from above, but either way, it might look something like this. They're telling us that this is true, and now they're telling us verify this fact. What it means is this: compute this limit and see that it is a 0. Why does that make sense? Well, the limit is equal to f minus L. So if you're computing your function f and then subtracting it from L, subtracting L from it, and you're finding a 0 in the limit, then that means that the two functions are approaching each other. They're getting closer and closer. This is what it means to have a slanted asymptote. It's a limit at infinity, but it's not that the limit is equal to a value. It's rather that the limit of the function minus a line is 0. That's the notion of slanted asymptote. But in terms of verifying, just like in this problem, they're just saying verify that it's true. Basically, it's saying compute this limit and see that it is a 0. So that's what I'm going to do, and that's very easy here. Find this limit. How do we do this? Well, the fraction here, f of x, this is certainly going to infinity. Looking at numerator over denominator. Numerator has the highest power. So this one is going to infinity for sure. Also the line 5x minus 5 is going to infinity because 5 times infinity is infinity. Then that's a problem for you if you try to do infinity minus infinity. That's indeterminate. You cannot say this is equal to 0 and that's it. No. What you have to do is transform this whole thing into one expression. In other words, I'm going to take a common denominator. Multiply this out to 5x plus 5 times x minus 1. Five x plus 5. Just checking the signs here. Minus 5x squared plus 5x minus 5x plus 5. That's good. Over x minus 1. You see that a lot of things are going to drop out. 5x squared minus 5x squared. And 5x minus 5x. So you are just left with 5 minus 4, 1, over x minus 1. What is the limit of this expression? As x goes to 0, sorry, to infinity, it's 1 over infinity. That's a 0. As we wanted to check, they said verify that this limit is equal to 0. So it really is. This is the only line, by the way, the only expression of the form ax plus b that you could have subtracted from f in order to find a limit 0. So this line can be called a slanted asymptote because f approaches it in the limit.